Dear participants of the National Day on Biomedical Engineering, today I will present you a method for exploring temperature gradients in infrared neural stimulation. First, a bit of context. Neurostimulation is widely used to treat chronic disorders such as chronic pain, neurodegenerative diseases, deafness, and epilepsy. However, neurostimulation suffers from shortcomings due to the use of electric current to stimulate the nerve. Recordings are polluted by stimulation artifacts. It lacks spatial resolution. Neurostimulators are incompatible with magnetic resonance imaging, and the order in which the nerve fibers are activated is not physiologic. Fortunately, optical stimulation could be a good alternative to overcome these limitations. Optical stimulation induces a neural response to a transient near-infrared light pulse. The most widely accepted hypothesis is that the nerve activation is linked to a photothermal effect. However, the characteristics of the spatiotemporal temperature gradients needed for the nerve activation are not well known. To better quantify these temperature changes, a first approach is the modeling of the light and heat transport through the nerve. A second approach is to measure experimentally the temperature change at the surface of the nerve. The method I propose here is the combination of the simulation of the spatiotemporal temperature gradients and compare the obtained results with experimental results. As preliminary results, the designed experimental setup is composed of an electrical stimulator and an acquisition chain to record nerve response to electrical and optical stimulation. The optical stimulator in purple is a near-infrared laser, and the infrared camera records the temperature at the nerve surface. Let's see what this setup looks like in real life. On this top view of the setup, you can observe the box containing the electronics of the electrical stimulator and the acquisition chain. The DAQ is used for the analog inputs and outputs management. The optical stimulator is on the left, and the infrared camera is placed above the dissected nerve. Now, if you take a side view of the setup, you are able to see the optical fiber which delivers light pulse to the dissected nerve. By taking a closer look on the stimulation site, you see the dissected nerve along which the action potentials are propagated. These action potentials can be triggered by the laser pulses or the electrical stimulator, composed of 2 electrodes. And 3 electrodes are used to record the electrical activity of the dissected nerve. The validation of the presented setup is in progress, and the infrared camera already allows us to have an idea of the characteristic times of heat diffusion when the nerve is exposed to the laser pulses as shown in this small video. Thank you for your attention, and don't hesitate to contact me if you have any questions.